All right. Well, good afternoon, I suppose, everybody. Welcome back. What we're doing today is something a little bit different, a little bit unique. We're actually going to be looking at multivariate tests as opposed to sort of the bivariate tests that we've been looking at over the past couple of weeks. So the main difference between a multivariate test and a bivariate test is simply a test which is relevant across more than just two populations. Okay, so I'll talk a little about that in just a second, as well as how we can do these bivariate tests in R. Have you sent an email with your YouTube video link? Yes, I have. If you haven't received it, well, you should have received it. If you haven't, let me see if I can get it to you right here. Okay, so that just means that you're not on the list. Okay, give me a second here and I'll get that to you. I think I probably did. Okay. All right. Well, in any case, it's fine because I'll paste it in the chat. Okay, so if you want to watch, you can jump onto that playlist, and the videos will come up with a bit of a lag. That's fine. Okay, just use that link. I won't send it again. Anyway, what was I saying? Multivariate tests. Okay, so let's talk a little about multivariate tests and why they're useful. Okay, so let me jump over to here, and we'll start off by talking about the most basic multivariate test, which is your simple means test. And we'll talk about how we can actually do a means test. All right, so let me bring this up right here, and we'll start talking about how we perform a means test. Okay. All right, so the first thing we're going to do is just talk briefly about what it actually means, and then we'll talk about how we perform these tests, including sort of what test statistics we use, what distribution we use, and we'll talk about how we can actually set up that test statistic and how we create that test statistic in the first place. So the idea here is that you have multiple populations. Okay, so let's say you have pen's not working. Give me a second here. I think that should make it work. That's the dead pen. This one's a good one. Yes. Okay. I have two. One's dead. All right. So let's say you have multiple populations. So you have K populations. Okay, so you have population 1 with mean mu1. You have population 2 with mean mu2, etc., all the way to population K with mean mu k. Okay? And what you want to know is you want to know if all of these mu's are the same, or if the means are different. Okay, or not all the same. This test right here is known as an ANOVA test. ANOVA, analysis of variation. Why is it called an ANOVA test? Where does the word analysis of variation come from? Well, it comes from the fact that this test right here depends on the variation within the group and the variation between the group. Okay, so what we're going to do is we define some quantity that's known as the total variation in the data, and we try to decompose this total variation into variation that is between group variation and within group variation. Now, why do we want to decompose this into between group variation and within group variation? Because what we're trying to do is we're trying to figure out the differences between these groups. Are they large or are they small compared to the total variation that we have in the data? Okay, so the idea here is that this between group variation represents systematic differences between the groups. Okay, so this is systematic. Whereas the within group variation represents some sort of a random variation. Okay, that's not systematic. You can't sort of attribute that to the grouping. Now, the idea is that if the between group variation is large, is proportionately large, then what that of course implies is that the means are likely different because it's systematic differences, right? So it means that there's systematic differences, and so the means are likely different. Let's call that case 1. Okay. Case 2 is if the between group variation is proportionately small. Okay, what does that imply? What that implies is that the differences that we see are likely random. Okay, random meaning that they're not attributable to the grouping. So that means that the means are not likely different. Okay, so if you want to visualize how these cases look, I'll give you an example. Let's take a simple example where you want to analyze whether the average mark in 2 classes is the same. Okay, and what you plot is the following. So let's say this is case 1. All right, case 1 is where the between group variation is proportionately large. So you have class 1 and the marks are around here. Okay, so this is, let's say, low marks, this is high marks. So you might think that this is something like, let's say 50, this might be like 100, okay? And then class 2, the marks are here. Okay, so the within group variation refers to how much variation there is within each class. Okay, so these here refer to within group variation. Okay, within each group. Now the between group variation represents the variation between each of these groups. In that case, this would be this right here. This will be the between group variation. And in this case here, you can see that the between group variation is actually quite large. Okay, and because it is quite large, you're likely to say that the average mark in these 2 classes are probably different. Okay. Now I'll give you another case, which is case 2, where it's the opposite situation, where the within group variation is larger and the between group variation is relatively small. So you have the first class. In the first class, let's say their marks are something like this. Okay. And the second class, let's say their marks are something like this. Okay, so therefore the within group variation looks something like this. You have this within group variation for group 1 here, or class 1, and you have this within group variation here for class 2. Okay, so this represents the within group variation. And the between group variation is probably something like this. Right, so those are the means, so it's probably represented by this amount right here. This is the between group variation, which you can see is proportionately very small compared to the within group variation. All right. Now in this case, the evidence for the means being different is very weak. Why? Because you can see that a lot of the variation is random, right? It's everywhere. It's within the classes. It's not necessarily between the classes, okay? So in this case here, you would say that the means are likely the same, okay? Or means not likely different. Whereas in the first case, this is where you would conclude that the means are likely different. Okay? Does that make sense to everyone? Give you thumbs up, thumbs down. Any questions? Yep. Okay. Yep. Good. Okay. So that's the general gist of what's going on. All right. Now let's actually formalize this into a test statistic. So the test statistic is as follows. Under the null, the test statistic for this type of test looks like this. Let me see here. I need the formula because of course I cannot remember this. F is equal to SST divided by K minus 1 over SSE divided by N minus K, where K is the number of populations and N is the sample size. Okay? This numerator here, this refers to between group variation, and this denominator here represents within group variation. Okay? So you can see that if the between group variation is proportionately larger, then that drives up the F statistic. Okay? So you can see here that if the between group variation is larger, that implies that the F statistic is larger, which implies, of course, that you're more likely to reject the null. Okay? Reject the null. Okay? So that's the point that we can see here. All right? So how exactly do we compute SST and SSE? Well, let's have a look at an example. And in that example, we'll talk about how we can actually compute these different quantities. Okay? So this is the crux of what's in part B right here. So let's have a look at the data, and I won't, you can read the data. You probably read the data description already, but let me just talk a little bit about what the data is about and what exactly it is that we're trying to do here. So I won't sort of read the story, but the main point is that you have these tobacco leaves, and these tobacco leaves are being tested, and there are 3 groups. And the difference between these groups is how much water is being given to these leaves. Okay, so group 1 receives the average amount of water, group 2 receives a little bit less water, and group 3 gets a little bit less water than that. And what we're trying to do is we're trying to compare the sizes of the leaves across these 3 different groups to see if the sizes of the leaves are the same or if the sizes of the leaves on average are different. So it's just a means test across these 3 groups right here. Okay. Excuse me. Okay, so let's have a look at the data file. And there's actually 2 data files here, nicotine 1 and nicotine 2. And the difference between these 2 files is that one is stacked and one is unstacked. Okay, so nicotine 1 is stacked and nicotine 2 is unstacked. And I'll sort of show you the differences. And they're useful for different things. You can always unstack data fairly easily, but it's nice when it's done for you. So let me just bring up the data file and we'll talk about how we can visualize this stacking. So I've got the 2 data files here, and they're ready to import. And I think nicotine 1 is the one that's unstacked, isn't it? Nicotine 1 is stacked. Okay. So let's call this T5S for stacked. And I'll create another one which is unstacked. And this is nicotine 2. Okay. So if you have a look here, what we're interested in is leaf size. And with the stats, right, you can see that you have a variable which represents the groups, and the leaf size contains all of the groups in one variable. Whereas with the unstacked, it contains it in 3 different variables, all right? So primarily for the first part, we're going to be working with unstacked data, and then when we talk about the Kruskal-Wallis test, which is like a generalized multivariate Wilcoxon rank test, we'll use the stacked data. But for now, let's stick with the unstacked data and start from there. Okay, so maybe you can start with a summary. And what we're really interested in are these three leaf size variables. They represent the leaf sizes with the different amounts of watering. And we can see here that with less watering, the means are indeed smaller. Okay, so the idea here is now trying to figure out whether this is random or whether this is actually something that's systematic. So in order to do that, we can perform an ANOVA test, and the syntax for an ANOVA test are quite straightforward. Okay, so you want to use summary and use AOV. Okay. Now to do the automatic test, we're actually going to use the stack data because that's how the inputs are used. So what you want to do is you want to put in the name of the variable you're testing, which is leaf size, put a tilde, and then put in the groups. Okay, so this is testing leaf size grouped by the variable group. And if you print that out, you can see here that this is the F statistic and this is the p-value. Clearly you reject the null because the p-value is less than 0.05, right? So the means are different. So that means that on average, if you give the plants different amounts of water, they actually give different leaf sizes. Okay. And the idea here is we're now trying to replicate this test, except doing it by hand to make sure that we can actually get the same F test statistic and the same p-value, okay? So let's talk about how we actually do this by hand. All right, so first of all, let's talk about variation. Variance is defined as follows. So the variance of x, let's say, is 1 on n minus 1 times the average squared deviation from the mean, okay? This component right here, that's referred to as the variation. Okay, so variation is not the same thing as variance. Variance represents the whole thing. Variation represents just this thing here. So you could think of the variation in x as the variance of x multiplied by n minus 1. Okay, of course that's fairly straightforward, all right? So what we're trying to do here is we're now trying to find the variation, or sometimes also called the sum of squares, for these three leaf sizes, okay? So what we're trying to figure out is the following. We're trying to figure out the sum of squares for group 1 of x1 minus x1 bar, where x1 bar is, of course, its mean, right? This is the variation, so you can just take n minus 1 times the variance of x1, right? And then similarly for x2 and x3, okay? So you can really see why these are within group variations, okay? Because you're measuring the variation, or the variance, if you will, within each group. Group 1, Group 2, Group 3, okay? And then the SSE, so let's call this SS1, this is SS2, this is SS3, okay? Then the SSE, which is going to form a part of the F statistic that we saw before, is simply the total of this within group variation, right? So you can really see how these all represent sort of within group variation. Okay, so the SSE is the total within group variation. It's SS1 plus SS2 plus SS3, all right? Now, of course, we can use R to figure out these quantities fairly easily, all right? So let's switch back over to R and talk about how we can figure these things out. So we have here the leaf sizes. So we can calculate the variance and multiply it by n, which is 50, in order to, n1, n2, n3, or 50, in order to figure out the variation. Well, I guess n minus 1 actually, so 49 to get the variation. Okay, so let's create n1, which is just length of T5 US, leave size 1. And I'll create n2 and n3, even though they're the same. It's good practice never to assume things, always to actually measure things. We have n1, n2, n3, they're all 50. Okay, so the first thing we're going to do is we're going to say SS1 is equal to the variance of leaf size 1 multiplied by n1 minus 1. Okay, and we'll do the same thing for SS2 and SS3. SS2, SS3. This will be leaf size 2. This will be leaf size 3. And N2 and N3. And if I run these, you can see here, we have the 3 sum squared variables. Okay? And of course, if you want SSE, that's just SS1 plus SS2 plus SS3. You want to print out SSE, you can just type SSE down here, and we get our SSE value, which is 6,694.70. Okay, so that's your value for SSE, 6694.70. Okay, so we can go back here and let's just jot that down. SSE. All right, what did we get here? We got 6694.70. And that represents the within group variation, the total within group variation. Okay. Now the next step is to figure out the between group variation. And in order to figure out the between group variation, we need what's known as SST. Okay. So I'm going to define here x double bar to represent the grand mean, the mean of all the x's. Then it's simply just n1 times x1 bar minus the overall mean squared plus n2 times x2 bar minus the overall mean squared plus n3 times x3 bar minus the overall mean squared. So you can see how SST represents between group variation. You're looking at the difference between each group and the overall mean, right? So it's not variation within each group, it's variation between each group, right? So we talked about how this quantity here represents within. This quantity here, SST, is going to represent between. Okay, and the F-stat is constructed with this within and between group variation. Okay, so x1, x2, x3 here, all really easy to calculate, of course, they're just means. And the grand mean is, of course, just the mean of the entire data set. So let's talk about how we can do that. You should all know how to calculate means now. So M1 is mean of T5 US, leaf size 1. Let's do the same thing for M2 and M3. So these are our means right here. If you want the overall mean, the way that you would have to do that, let's call this mean G for grand mean. How would you do that? I would do just combine. So C is combine, and I'll combine leaf size 1, comma, leaf size 2, comma, leaf size 3. There's probably other ways of doing it. This is how I would do it. So all this does is it calculates the mean of the combined series of leaf size 1, leaf size 2, and leaf size 3. Okay, so you have the 3 means here. Now, all you need to do is just type in the formula that we had before, which is N1 times M1 minus Mg all squared plus N2 times M2 minus Mg all squared plus N3 times M3 minus Mg all squared. Okay, type in here SST. And 1270.51 is our SST. So we can write that down over here. So let's switch through back over here, and we can calculate this to be, what was it? 1270.51. Okay, now from here it's fairly easy to calculate our F statistic. So before I do that, do you have any questions about what we've done so far? Are we all good? Give me a thumbs up if that's all good. Yeah? Okay, looks like you guys are pretty happy. So the idea here is we figured out the within group variation and the between group variation, and now we just need to normalize it, right, to calculate our F statistic. So remember the test that we're trying to do here. Okay, the test that we're trying to do is the following. H0, mean 1, mean 2, and mean 3 are the same, whereas H1, one way of writing it is something like this. All right, so under the null, the F test statistic is equal to, I don't remember this, so I need to look it up, SST divided by K minus 1 over SSE over N minus K. Okay, K here is equal to 3. All right, so let's put the numbers in and we'll get R to do it for us. You don't have to do it manually at all. So N is just the total N, that's N1 plus N2 plus N3, and K is equal to 2. Oops, no, K is equal to 3 because there are 3 populations. Okay, so F is equal to, actually let me call it F stat, because if I type F, you can see how F has this sort of purple color. It means that it's reserved, so you have to use something else. Let's call it F stat. Numerator, SST divided by K minus 1. Okay, divided by denominator, SSE divided by N minus K. All right, so what's the F stat? 13.95, which seems to be the same F stat that we got before, and that's pretty promising. 13.95, let's write that down. Okay, which is the same as the F stat that we got when we did it automatically. All right, so here you have two choices. You can say, well, you reject H0 if F is greater than the F critical value. Okay, let's say at 5%, or you can reject H0 if the p-value is less than 0.05 at 5%, okay? Either are fine. These are actually equivalent statements, okay? Why are they equivalent statements? Because one is comparing the x value and one is comparing the area. So the F stat looks something, F distribution looks something like this. So what you're basically saying here is, if this area is 5%, this is F crit, okay? So saying that F is greater than F crit, or saying that the area to the right of F is less than 5%, all means the same thing. It means that the F test statistic has to be within that rejection region. Okay, so you can make a statement about the areas, which is F is greater than F crit, so it's to the right of F crit, or you can make a statement about the areas, which is the p-value. So if p is less than 5%, of course, it means that it has to be to the right of F crit as well for that area to be smaller than 5% if the area at F crit is 5%. Okay, so they're interchangeable. One's talk about the areas, one's talk about the x values. All right. Okay, let's go back here. If you want to calculate the p-value, let's see if I can remember this. It's pf. And you put in here the F stat, comma the degrees of freedom, so k minus 1, n minus k, and lower dot tail is equal to false. That looks right. Okay, so this is the p-value here, all right, and that p-value is really small, 2.84 by 10 to the negative 6, which is the same p-value as we got when we did the test using R, which is this output up here, 2.84 by 10 to the negative 6. Okay, so I think we can write down our conclusion. Whenever you're doing a test, you always want to make sure that you write down your conclusion. So here you could say that the p-value is equal to 2.84 times 10 to the minus 6, whoops, which is of course smaller than 0.05. Therefore, the conclusion is that you reject H0 at 5%, and you conclude that the means are not all the same. Okay, whenever you're doing your conclusion, you always want to make sure you have these three things. Okay, the first thing is you want to have p less than 0.05. Okay, second thing is you want to have, that means you reject. And the third thing is you want to have the interpretation. What does it mean to reject the null, right? So you have to have all those three things when you're doing your conclusion of your test, all right? So I think that's an example of how you do the ANOVA test. Do you have any questions about the ANOVA test before we move along and look at the, let me bring up the chat in case you guys had any questions. Before we move along to looking at the Kruskal-Wallis test, we all good? All right. Let's move along and have a look at the Kruskal-Wallis test then. So if the ANOVA test is like a multivariate means test, then the Kruskal-Wallis test is a multivariate Wilcoxon rank test. So it's a median test, basically, okay? So let's talk about the Kruskal-Wallis test. So the Kruskal-Wallis test is similar, except it does the following. It tests the location of population 1 to etc. all the way to k is the same, where location really refers to median. Okay, you can use those terms interchangeably. And H1 is at the location of the populations 1 to etc. all the way to k are different. All right. So the Kruskal-Wallis test uses the following test statistic under the null. This quantity, which is called H, is equal to 12 over n times n plus 1 times the sum from j is equal to 1 to k of tj squared over nj minus 3 times n plus 1, where n is the overall sample size. So n is just equal to n1 plus n2 plus etc. all the way to nj, or nk I should say, because you have k groups. And tj is the rank sum defined in the same way as the Wilcoxon rank test of group j. So if you can calculate the rank sum, you should be able to calculate the test statistic H. So what we'll do here is, let me just jot down the test specifically that we're trying to do here. So you're still using leaf size. So location of groups 1 to 3 of leaf sizes are the same. And the same thing except different. Okay, so what we need to do here is write down under the null, this H is equal to 12 over n times n plus 1 sum. Actually, don't need the sum, we can just write it down. T1 over n1 squared, I should say, T2 squared over n2, and T3 squared over n3, because you only have 3 groups. Minus 3, n plus 1, right? Yes. Okay. Alrighty, well, let's skedaddle along here. So what we can do here is we can start calculating these rank sums. Now, in order to do that, we actually need to use the data set where all of the variables have been stacked. Now the reason why is that you can't calculate the rank sums, or you can't calculate the ranks, I should say, when you have the variables separate like this. Because if you calculate the ranks when the variables are separate, the ranks will be incorrect because the ranks will only be on those 50 variables, not on the 150 entire variables when they're stacked, okay? That's why we need to use not the T5US, but T5S to get the ranks. Okay, so what I'll do here is I'll cross-call Wallace test. So what we'll do here is we need to, first of all, create the ranks. So T5S ranks is equal to T-rank, T5S leaf size. This creates the ranks, and now we need to separate the ranks out by group. So the way you do that is by creating the group variables. So T5S, let's say group 1. So you see here, group is equal to group 1, group 2, so on. So what you can do here is T5S group is equal to, in quotes, group 1. And like we said last time, you need to multiply it by 1 in order to convert that to a 1 or 0. So a binary indicator as opposed to something that is either true or false. And we can change this for group 2 and group 3 as follows. The reason why we do that is we can now get the ranks for each of these three groups. So T5S, say rank 1, is T5S ranks multiplied by T5S G1. So by multiplying, you only select the ones where the group is equal to 1, so where it's in that correct group. Okay, in group 1, group 2, and group 3 specifically, not the entire rank series. It only selects it when it's equal to 1, right? So that's what this does. And what you've got now, rank 1, rank 2, rank 3, is of course going to be the 3 ranks of these 3 groups. Okay, so the rank sums, R sum 1 is the sum of T5S rank 1, and do the same for 2 and 3. Okay. And you have here your 3 rank sums. Okay. Fantastic. So once you have these 3 rank sums, you can calculate your H. Okay. So let's just briefly review how you calculate the H. So that's this quantity right here. So just using this formula here. And what I might do is I might create N is equal to N1, oops, plus N2 plus N3, because that's quite useful. We use that quite a lot. Okay, so H, I'll call it H stat because I don't think we can use just the letter H. So H stat here is going to be equal to, open brackets, 12 divided by N times N plus 1. That's the first fraction. And then multiplied by, open brackets, T1 squared, so that's R sum 1 squared, divided by N1, plus rank sum 2 squared divided by N2, plus rank sum 3 squared divided by N3. Okay, and then just minus 3 times N plus 1. That looks pretty good to me. Let's run that and see what H stat is. Whoops. H stat. 22.40. That's your H statistic here. So I think we can go back and you can write down that our H statistic is 22.40. Okay. So now the same idea, right? You can calculate the p-value. And if the p-value is less than 0.05, you reject the null at 5%. All right, so what's the p-value? Well, you have to use p chi-squared because this quantity right here, this H statistic under the null, it follows a chi-squared distribution with k degrees of freedom. Actually, k minus 1 or k? I don't remember. I need to check. I think it's k. follows a chi-squared with k minus 1. So my instinct is correct. It's always k minus 1 degrees of freedom, okay? So in order to get the p-value, you need to use p chi-squared. So here you can use p chi sq. Okay, so for the chi-squared distribution, the input is h stat. Degrees of freedom is k minus 1. And lower tail is equal to false. Okay, so this right here is going to be your p-value, 1.37 by 10 to the negative 5, a really small number. Okay, 10 to the negative 5, which is less than 0.05. All right, so therefore you reject H0 at 5%, and therefore you conclude that locations of leaf sizes in groups 1, 2, and 3 are not the same. All right, are not the same. So that's how you would conclude that. Let's do it by hand. Let me show you how to do the Kruskal-Wallis test in R. It's actually really easy to do the Kruskal-Wallis test in R. So to do the Kruskal-Wallis test, it's Kruskal.test, I think. Kruskal.test. Yes, that's right. And you have to use this S series, so stat series, and it's the same input as with the ANOVA test. So it's the variable you want to test, so T5S, leaf size, and then tilde, the grouping, which is T5S group. Okay, and you get the Kruskal-Wallis test here, and you can see that the test statistic is 22.4, which is the same as our H statistic. And the p-value is 1.37 by 10 to the negative 5, which is the same as the p-value that we got calculating it by hand. So it verifies that we can get the same result as R by computing it by hand. Okay? All right, so I think that's the main gist of what we're working with today. If you understand the Kruskal-Wallis test, you understand the ANOVA test and sort of the ideas behind why they work, that's all you need to know. So if that makes sense, then that's all fine and dandy. If you have any questions, let me know. Otherwise, we can finish here, and I'll see you guys again on Friday. Now, in the exam, do we do the questions on R or by hand? That's going to depend on the nature of the question. So it depends on what the question asks you to do, how much the question's worth, what steps you're asked to show, so on and so forth. But regardless of whether you do it in R or you do it by hand, you always need to make sure that you're following the correct steps. You need to list out your hypotheses, you need to list out what distribution, your hypotheses, test statistic, what distribution that test statistic follows, what the actual value is, or p-value, and then you write your conclusion, like I said before. How you get the test statistic, that's the difference, right? That depends on the nature of the question. All right.